Welcome back to CST432. Today we will go into how to break up our main problem into smaller parts so we can solve it. So this is called Divide and Conquer Part 1. Some of the key concepts we will look into today is, first of all, what is behavior-based robotics. Then we'll delve into how we can use stacks and passing parameters through the stacks. Next, we will look into how to interface C and assembly language routines in the same program. And finally, how all these routines will be built out into modules and software libraries. First of all, what is behavior-based robotics? In behavior-based robotics, we divide up the task performed by a robot such as a tribot into smaller tasks. Most of these tasks can be performed in parallel. Examples of this are sensing of objects in the environment, following a line on the ground, as well as avoiding obstacles. So behavior-based robotics addresses these issues via parallel yet simple routines that operate together to solve the problem. This is an example of a behavior-based robotic framework. On the left, we have the inputs such as sensors. Sensors may include light, sound, as well as touch sensors. In the middle are what is termed behaviors. They operate in parallel and they have a priority. From the top to the bottom, there's the highest priority behaviors are placed at the top and the lowest priority behaviors are placed at the bottom. Now these behaviors operate concurrently, meaning that they are working at the same time to solve a problem. And finally, the behaviors will generate output that will affect the behavior of the actuators, such as the motor for the wheels, or the speaker, or any other actuators connected to the robot. So, for example, a behavior such as avoid objects can cause the motors of the wheel to turn to avoid colliding with an obstacle. Whereas identify object may use a camera or some other device to capture the image from the object in front of it and try to make sense of it. And this again may cause the robot to move forward towards the object. This is an example of a BBR control architecture for a robot. On the left, we have the inputs from sensors such as a touch sensor, a light sensor or photocell, as well as infrared detectors. Now, these sensors feed into the various behaviors to allow the behaviors to make decisions regarding possible output values for the actuators, such as the left and right motor controlling the wheels that is controlled by the controller. Now the behaviors compete with each other. So the arbiter's role is to decide among the competing behaviors to determine which is the appropriate or winning behavior so that their outputs may be programmed into the controller itself. In terms of the software architecture, we can decompose the task into several modules. And these modules represent a group of related routines that achieve a particular goal based on the input requirements. Now routines obviously have to have inputs that are passed to it to affect its behavior or the operation, and this is done by passing parameters from the calling routine to the called routine. In the ARM architecture, there is an AAPCS convention that can be used for interfacing the calling routine to the called routine, and these define the order of the parameters in the registers, as well as any additional parameters that do not fit into the registers will be placed on the stack for passing into the called routines. We will first look at the conceptual stack. In a stack, what happens is that you have items that is put into the stack using an operation called push. This will add an item to the top of the stack. The reverse operation to remove an item from the top of the stack is called pop. Now in reality, we do not actually insert and remove objects from a software stack. Instead, what we do is that we use a pointer to indicate the top of the stack, and where the pointer is will be the item that will be pushed on top of or popped from the stack as appropriate. Now we would like to look at how we can implement a conceptual stack in a software mechanism. This description is a full descending stack, meaning that the stack will start from a high memory address location and move towards a low memory address location. So we use a pointer, which is called a stack pointer, which has a value that is the address of the empty stack will be the bottom of the stack. Now we look at what happens to the stack when we push an item into it. Now the stack is upside down in the sense of having the bottom of the stack at a higher memory address, whereas the top of the stack is moving towards the low memory address. So physically we can think of it as being an upside down device, but it's because we are dealing with software, we do not have to worry about things like gravity. So it will not pop out or fall out of the stack accidentally. So in this case, when we push an item into the stack, the first item will therefore move the stack pointer to a value such as FFFFC, which is the number of bytes needed to store a 32-bit variable. Now this variable will be pushed into the stack, and starting from the stack pointer at FFFFC, it will have the least significant byte followed by the next highest significant byte, and finally at the highest address location, the most significant byte of that 32-bit value. So in the example here, we are pushing the hexadecimal value 31AF2BCD, and in the memory address locations, at the lowest value memory address location, we have the byte CD. The next higher value is 2B, the next higher AF, and finally the highest location has the value 31. Now this is the implementation of a full descending stack using a little endian processor architecture. Now when we are using stacks, we need to be careful about the number of push and pops that are present in our code. So in other words, we need to balance the number of push and pops. Here in the first highlighted section, we notice that in subroutine 1, we push the registers R4, R5, R6, R7 and R8 given in the first push instruction. So this instruction is actually equivalent to the ARM instruction STMFD, and push is used as a short an alias to that instruction. Now at the end of the subroutine, we will pop out the same number of registers from the stack. In this case, pop R4, R5, R6, R7 and R8 given by the last instruction in the highlighted section. Now what happens if we do not balance the number of push and pops? Now this example here for subroutine 2 is an example of an unbalanced stack usage, where we push in only one register R1, but at the end of the section we pop out two registers R1 and R2, or put values into both of these registers from the stack. Now what happens in this case that we will cause a stack underflow if the last item in the stack was popped off, meaning that there's no more items in the stack, but we try to remove an additional item from the stack. This is called a stack underflow condition. Alternatively, there may be an unbalanced stack usage condition where we push in more variables into the stack than the number we pop out. In this case, in subroutine 3, we push in two registers, but we only pop out one. This is going to cause garbage to be left on the stack, and this prevents access to the subroutine return address if we are doing this from within the subroutine. Now, as I mentioned, if we do not balance the number of push and pops into the stack and out of the stack, we will cause problems with our program in an unexpected manner. Next, we look into how a program can call routines. Routines can save space if you have a specific algorithm or lengthy sequence of code that is used frequently. Instead of repeating it in the program multiple times, people create a routine that has the common instructions and then pass in appropriate values to for the routine to operate on those values and generate the outputs for use by the rest of the program. So there are two types of routines that we can write. The first type of routine is called a leaf routine, which are self-contained routines which do not depend on or call other routines. So this type of routines, such as leaf routines, can be accessed using routine linking. Now, the second type of routines are what is called known as non-leaf routines. Non-leaf routines can call other subroutines and therefore must be accessed using subroutine calls, which involve the storing of the return address on the stack. Here in this diagram, we see in the main program there is a call to subroutine 1 using branch and link. Upon execution of the branch and link instruction, the first thing the processor does is to store the return address, which is given by the label return address 1, into the link register, otherwise known as R14. Next, the microprocessor will then update the program counter to have subroutine 1 starting address as the next instruction to execute. It will then enter subroutine 1, execute the instructions in there, and finally, at the end of the subroutine, there is an instruction which will move the link register value back to the program counter. Now, as we remember, the link register value contains the address for return address 1. So subsequent to that move instruction, the next instruction to be executed will come from the return address 1 location. Now let's look at what happens if we try to call a different subroutine from our original subroutine 1. In this case, in subroutine 1, we will try and perform a branch and link instruction to subroutine 2. When we execute the branch and link instruction, we will then store the return address 2, which is in subroutine 1, into the link register R14 before we transfer execution to subroutine 2. Once we get into subroutine 2, we can execute the instructions there, and finally at the end of the subroutine 2, we will again use move PC, LR to change the program counter value back to the value stored in the link register, which in our case returns us to return address 2 inside subroutine 1. So far so good. But what happens when subroutine 1 reaches its end of its subroutine and then tries to return back to the main program? The move PCLR in this case, in terms of the link register value, only contains the value for return address 2. When we try to return to the main program, this will cause an endless loop because there's no way for us to reach the main program without the return address 1 in the link register. Now let's look at how we can perform the subroutine call to subroutine 2 safely. This is called non-leaf routine calls. In this example program here, at the beginning of the main routine, we see there's a branch and link to subroutine 1. So far, so good. Then in subroutine 1, once we enter into the subroutine 1, we will see the push instruction. Here it is important to note that in addition to any register values you want to preserve, such as R4, R5 and R6, we also preserve the link register value. The link register being pushed onto the stack is an important part of a non-leaf routine call support. Eventually, we come to the instruction that calls subroutine 2 using the branch and link to subroutine 2. In subroutine 2, we again do something similar. We preserve any registers that is needed by subroutine 1 that is modified here in subroutine 2, as well as the link register. Now, if subroutine 2 does not call any other subroutines beyond itself, then we actually do not need to store the link register value. But to be safe, we do it anyway. This allows us to update subroutine 2 in future without worrying about having to update the push instruction as well. Eventually, we reach the end of the subroutine and we will pop the value of the link register straight into the program counter. This will allow us to transfer its call back to subroutine 1 in one instruction. We then continue execution of the rest of the instructions in subroutine 1. Eventually, we reach the end of the subroutine 1 and we see a pop instruction here. In this case, we are popping the link register value back into the link register itself. This is an alternative way of performing the restoration of the value in the link register. You can combine it together with the in the same way that is done in subroutine 2, but here is separated to illustrate the process more clearly. So first we pop or restore the values from the stack into the registers that we want to preserve, including the link register, and then we transfer that value into the program counter to return to the main program. In the main program, we also perform a direct call to subroutine 2 for illustration. Here we will make use of what we have learned about subroutine calls to implement a simple recursive routine. So factorial of a number is defined by the value of the number multiplied by all previous integer values preceding it, and finally the multiplication of all these values is the result. So n factorial can be implemented using a routine that calls itself in the following manner. We pass in a parameter n, which is the value we would like to compute, and we do it by multiplying the value of n with the factorial of n minus 1 to result in the final answer. Obviously, when we try to calculate factorial n minus 1, we need to call the same routine again, passing it now the value n minus 1. And within the call for n minus 1, we return the value of n minus 1 multiplied by factorial of n minus 2, and so on. This is what is meant by recursion. Here we look at how this is implemented in assembly language. At the beginning, there are the comments indicating that on entry to the routine, we have a parameter n in register R0. On exit, R0 will contain the result of the calculation of the factorial of that number. As always, we need to preserve any register that is modified by the routine that is not the one of the argument registers such as R0, R1, R2 or R3. In our case, we need to preserve R4 because we use it to keep track of the current value of n for the calculation purposes, as well as the linked register value, which is important for us to be able to call factorial from within factorial itself. First of all, we take note of the fact that n factorial eventually comes down to n multiplied by n minus 1 factorial, and the last value that we can calculate is for 0 factorial. By definition, 0 factorial is equal to 1. So we will first check the input value in R0 against the value 0, and if it is 0, we will return the value 1 immediately. If it is not 0, we will then need to find the factorial value for n minus 1. In this case, we keep n in register R4, and then we calculate n minus 1 and store it back into R0 so that we can call the factorial routine using the parameter in R0 of value n minus 1. After we receive the return value from the factorial subroutine in R0, we will then multiply it with the existing value of n in register R4, and the final value of this multiplication will be stored into R0 for return to the calling routine. So at the end, we will then pop the register value for R4 since we have modified it in our subroutine, and as well as to pop the value of the ring register into the program counter so that we can return execution immediately to the next instruction in the calling routine. Now we look into how we can deal with parameters. As we've seen in the previous example for factorial, we have already used R0 to pass a parameter from the calling routine into the called routine. Now, the results of computations also will need to be returned to the calling routine, and typically there is only one value that is returned by the routine, which is stored in the register R0 before returning. The AAPCS defines a parameter passing convention for the ARM EABI standard, and this is the convention that we will follow in the rest of our discussion. First, look at what are the possible ways you can pass parameters. The first way is called memory-based parameter passing. Second, register-based parameter passing. Third, stack-based parameter passing. And fourth, the frame-based parameter passing technique. The first technique, memory-based parameter passing technique, uses predefined memory address locations for storing global parameters. These address locations are known to all the routines that use them, and therefore the memory usage convention is needed to make sure that the routines do not use the same memory address location for storing different variables, because inevitably we may overwrite the variable with incorrect values. Now, if we use memory-based parameter passing approach, it is very difficult to write recursive routines for memory-based parameters, since you may end up using the same location over and over again, such as for the factorial routine. But unfortunately, we also need to keep the previous value for the value n before we can calculate the multiplication of those values with the factorial result. Finally, it is strongly discouraged because it does not lead to reusable code. If we use a given routine using a memory address location A, and a different routine written in a different program uses the same memory address location A for different purpose, we cannot combine these two routines together into a new program. Now, the second approach is called register-based parameter passing. Now, you can use as many registers as available in the microprocessor for passing parameters from one routine to another. However, if we do that, we find that we may end up not having enough registers to keep our temporary variables for in our main routine before we call the subroutine. So in the AAPCS, only 4 parameters are allowed to be stored in registers directly. So in our case, if we use a register-based parameter passing technique, we can do so only if the number of parameters are less than 5. And the parameter types must be simple, such as integers or 32-bit values, or less than 32-bit values such as half words and bytes, or else pointers. Now, if you want to use complex data, for example, a data structure that contains different elements to be passed to the called subroutine, you would need to use a pointer to that data instead of the actual data itself. So this is called pass via pointer or pass via reference. So in the AAPCS, registers R0, R1, R2 and R3 are defined for use. And in such a case, register values in those registers are not preserved by the called subroutine or in the on return. Now if you pass parameters in other registers, this becomes non-AAPCS compliant, and you have to be careful when you do that to make sure that all your routines that use this technique are able to preserve the relevant register contents. The next approach is called the stack-based parameter passing approach. In such an approach, we will push the parameters onto the stack and then only after that call the routine. The parameters on the stack are accessed via a pointer. Now if we do this, we also need to define a stack usage convention. Do we push in the parameters from the first parameter specified for the subroutine to the last, which is known as first to last order, or do we use the last to first order where we push in the last parameter on for the subroutine into the stack first and followed by the earlier ones and all the way until the first parameter. That approach or convention depends on the language that we use. In C, it uses the last to first order. Another thing to note about the parameter passing using the stack is that it is an asymmetric approach. We can push parameters into the stack to be passed into the called routine, but we cannot return parameters via the stack. Right? So the only way you can return a parameter is through the register, and typically only one register is used, which is R0. In this diagram, we illustrate the calling of a routine which requires three arguments: arg1, arg2 and arg3. In the first highlighted section, we notice that when we push the arguments into the stack, they are pushed in the last to first order. Arg3 goes into the stack first, followed by arg2, and finally arg1. And at the end of this sequence of pushes, the stack pointer points to the top of the stack, which is at argument 1. Next, we call the routine. As we remember from previous discussion, once we enter into the subroutine, we will need to preserve the registers that we want to preserve, as well as the link register value. In our case, we assume that we do not need to preserve any additional parameters on the registers, but instead only need to preserve the link register value, or else known as the return address value. So at this point in time, in the stack, we have the arguments as well as the link register value. Now let's see what happens if we try to return the value through the stack. We will push that value into the stack, but immediately after we do so, we realize that the stack pointer is now pointing to the return value and no longer to the link register or the return address value. So in this case, what do? We cannot return to the calling routine, and then this is the reason why we cannot use the stack to return parameters to the call routine. To summarize, when we want to perform a stack-based parameter passing procedure, we will first place parameters on the stack based on the stack usage convention. We then call the subroutine, and at the end of the subroutine, after returning from it, we will clean out the parameters that we push into the stack. Remember the need for balance of the number of push and pops. This is why this occurs. And finally, after we clean up all those parameters we push into the stack for calling the subroutine, we are then ready to return from our current routine to the parent based on the return address in the stack. Now the AAPCS defines the stack is used only if we have 5 or more parameters that need to be passed to the subroutine. The reason for this is that the first 4 parameters are placed in the registers. This speeds up the routine calling process tremendously. Only if the number of operands or the parameters that need to be passed exceeds 4 parameters, only then is the stack used, and it will provide us the flexibility of speed versus the number of parameters that can be supported being more than 4. And in the stack, the items are placed in the last to first order based on the C convention. The next technique is actually based on the stack-based parameter passing technique. However, it is different in the sense of having an additional step. This is called a frame-based parameter passing technique. Now, why do we need to do this? The reason is because after we push the number of parameters in the stack, we call the subroutine, and from within the subroutine, we may add additional items onto the stack before we are ready to use those parameters that we are passed into it. So the number of items on the stack after entering the routine depends on whether the link register and other registers are preserved. If none are preserved, then the value at the top of the stack is the parameters that have been passed in. If some of the registers have been preserved, including the link register, these locations will have changed. Therefore, there is an inconsistency in how we reference the parameters on the stack depending on how many items we want to preserve in our subroutine. To avoid this problem, we can use a dedicated register pointer known as a frame pointer to access the arguments in the stack that has been passed in. So in this case, the frame pointer always points to the preserved link register item on a non-leaf routine, or else the preserved frame pointer value in a leaf routine in the stack. This diagram illustrates a stack dump from a frame pointer passing technique for a non-leaf routine. So the frame pointer in the ARM processor is using R11, register 11, for pointing to the stack, and the value in the frame pointer is pointing to the return link register value. Now we know that if we use a frame pointer offset 4, which is 4 bytes above the current address for frame pointer, we will always be accessing the argument 5. Frame pointer with offset 8 will always access to argument 6, and so on up to the maximum number of arguments we have defined for the subroutine. Now if we use the frame pointer and go down in memory, then we will see the preserved values that have been put into the stack, including any local variables we may want to use in the subroutine itself that is stored in the stack for temporary storage locations. So how do we actually use the frame pointer based parameter passing technique? If we have a non-leaf routine, the first thing we do is to preserve registers, including the frame pointer and the link register value. Next, we will need to increment the frame pointer with the stack pointer address value by the number of items we pushed in less 1, and this will allow us to therefore point to the link register in the stack. Now for the leaf routines, we do not need to preserve the link register, so in such a case we need to push only the frame pointer value, and we then copy the stack pointer address value into the frame pointer without changing this value. So we do add fp, sp, constant 0. Now we need to adjust this value based on the number of other registers we push into the stack, so the value will be multiples of 4, which indicates word size 32-bit values that have been pushed into the stack. So the advantages of using the frame pointer is that we can always access argument 5 at frame pointer, constant value 4. Argument 6 is always a frame pointer, constant offsets 8, and so on. Of course, there is a cost involved. Additional instructions are needed for setup and for removing those values from the stack. And secondly, we also use this one register for stack frame access. This will not be available for other users within our routine. And finally, there's additional cost in terms of the memory slot needed in the stack for preserving the frame pointer itself. Now there's another benefit of using the frame pointer based technique in that we can use it for debugging. The frame pointer always points to the current stack frame in memory. At the same time, one of the items in the stack frame is the previous frame pointer value. This allows us to do a stack backtrace, meaning to follow the calling chain from the subroutine to the parent routine to its parent routine, and so on all the way back to the main program. Next, we look into how we can interface modules. Modules allow existing software to be compiled into object code libraries. They can be written in different languages such as C and assembly, as well as other higher-level languages which we are not covering in this course. Now, interfacing C and assembly modules allow for greater flexibility in development. We can use C for complex data structure manipulation, such as structures and other more advanced access combination of data items that are put together into a structure definition. Now, we can use assembly for speed, especially if we know that the routine generated by this compiler is not as efficient as it could be because it's not using some dedicated instructions that is available in the assembly language for us. First, we look at how we can call assembly from C. Here there's a function definition memcopy.h, which allows us to define a routine called memcopy_arm that will be called from our C program. So in this C program, we will include the header file for memcopy.h and call the routine memcopy_arm with the appropriate parameters. In our case, we need 3 parameters: outbuff, inbuff, and end. Here we shall look at the code for memcopy, which is written in assembly language. So at the beginning of the program routine, we notice the comments regarding the parameters that is passed into the program, into the routine, which is R0, R1, and R2, and on exit we return a pointer in R0. Next, we declare the routine memcopy_arm as a function type. This is needed by the linker to recognize that this is a function and should be treated as a function. We also need to declare it global for the linker to recognize that this is accessible from outside of this module. As always, we first must preserve any register we want to keep. In our case, we want to preserve R0 and the link register. R0 because we want to have a pointer to the destination buffer that is usable by the calling routine. Next, we will perform the process of copying the bytes from the source buffer to the destination buffer. In this case, we use R3 as a temporary register value to load the byte value from address given by the pointer in R1 and stored into the address given by pointer in R0. Now in both cases, we auto increment or post increment the value in R1 and R0 to point to the next byte in that buffer. Then we will decrement the counter value by 1 and check to see if it is still non-zero. As long as it's non-zero, we will repeat the copying of the byte values from the source to the destination buffers until the counter reaches 0. At the end, we will restore the value in R0 to the original address pointer value as well as the linked register value into the program counter so that we may return to the calling routine. Now, when we call C from assembly, we need to do a few more things. First of all, we use an intra-procedure call register to store the stack address pointer value. Now, after that, we need to align the stack pointer to the 8-byte boundary so that it can become AAPCS compliant before we enter the routine. This is achieved by subtracting the stack pointer value by the number of arguments, which is, if it is greater than 4, and multiplied by the number of bytes for each argument, which is 4 bytes per 32-bit value. Then we must round it down to the 8-byte boundary by clearing the lower 3 bits in the finalized stack pointer address. When we've done this, we will then have the original stack pointer value in IP, and the required parameters are placed in the stack at this aligned boundary. After the subroutine call, the stack pointer must be restored to its original value. This is accomplished by loading the original value of stack pointer directly from the stack using load register SP given the current SP value and the number of arguments offset from the included as the offset, and finally the new value or the old value of SP will be stored into the current SP so that the stack pointer is restored to its original form. To illustrate this of calling C from assembly, we will use a routine called send2. Send2 is a C socket library routine for accessing to the network. In this case, the send2 routine requires several arguments that is passed into it, and we will define in memory these arguments as locations in address given in the data section, and we see that they correspond to the appropriate parameters that's passed to the send2 routine. Then in this fragment, we see that at the beginning we assume that somehow stack pointer has already been initialized and it is word aligned, meaning it is pointing to a correct value in memory which is corresponding to the stack. Secondly, the intra-procedure call scratch register or R12 will be used for keeping the stack pointer value before the subroutine call. First thing we do, we notice that there are 6 arguments for the send2 subroutine. In this case, first of all, we will preserve the stack pointer value in the intra-procedure call register IP. Next, we will need to allocate 3 word size items onto the stack by subtracting the stack pointer value with 3 items multiplied by 4 bytes per item. This will allow us to point to the new value on the stack for keeping 3 items on the stack. Next instruction, we align the stack pointer to an 8-byte boundary by clearing the least significant 3 bytes of the stack pointer address value. Next, we need to initialize the values to be passed into the calling to call subroutine send2. First, we load the destination address pointer so that we can retrieve the value into R0. Okay, we use the same register for the address as well as the value itself to save on the locations that we have modified. Secondly, we will get the destination length, and that is stored into R1. And this then will allow us to push or store these values into the stack at the current stack pointer value, which is 8-byte aligned, by pushing or storing R0, R1 as well as IP into the stack. Now note that we do not update the stack pointer because we already previously changed it using the subtract instruction to move it to the new bottom of stack or top of stack address location. So when we use STMEA, which is equivalent to STMIA, it stores argument R0 or argument 5 at the stack pointer address, argument R6 or in register R1 at stack pointer plus 4 offset, and finally the original value of the stack pointer before we did all this manipulation, which is currently kept in the intra procedure call register IP at SP plus 8. After configuring the stack parameters, we then configure the various arguments, the first 4 arguments in the registers R0 to R3, so that we are ready to call the subroutine. Finally, we call the subroutine using the branch and link instruction. After the call to send2, we would then need to clean up the stack. In this case, we do so by loading the previous value of stack pointer directly into the stack pointer itself from the SP plus 8 offset location. Now that we've learned how to call routines and pass parameters, we look into how to convert algorithms into routines. First of all, if your algorithm uses any variables and they are global in nature, they must be converted into local or else known as stack-based or register-based variables. Secondly, we must initialize the variables when calling routines, which are either passed as parameters or else they have to have some default values. Registers categorized as preserved in the AAPCS standard must be pushed into the stack before being used as temporary variables in your routine. Okay. Finally, values in registers must be returned to original values using the pop instruction before exiting the routine, and the whole point of this objective is to make the routine both relocatable as well as re-entrant. Relocatable means that we do not depend on a particular memory address location for it to function properly. Re-entrant in the sense that we can call the routine multiple times. For example, if it is recursive and it still function correctly. So what's the objective for all this? It is for us to be able to develop modules and software libraries that can be reused. Now the items that we should take care of when we are doing so, first of all, we want to maintain cohesion. The routines in a module or library should address a common functional area. For example, dealing with input and output processing or string manipulation. Secondly, there should be minimal coupling or no coupling. You try to have libraries that do not depend on other modules if at all possible. Thirdly, we should be consistent in the way that we call a subroutine. If you pass a parameter for a group of functions, the first parameter should have the same format as the other routines if they have the same requirements. The ordering of the parameters should be consistent as well. Fourthly, there should be relocatability, meaning that there are no hard-coded addresses. If at all possible, we should use relative addressing where we use a offset from a parameter that is passed into the routine for accessing any given memory address location. Lastly, reentrancy, where we store the variables on the stack as local variables if possible, so that if we call it from an interrupt or else in the preemptive multitasking system. Those routines can be called multiple times without affecting each instance of that routine call. For further information on the AAPCS as well as behavior-based robotics, here are the references they can look into. Now, see you next time when we talk about how we can make use of this to implement a robot that performs the grasping action.